Okay, we are going to work on factoring the GCF out of a polynomial. Okay, so we're focusing on polynomials, and we're going to begin factoring a GCF out of a polynomial. Now, in order to do this, we need to remember GCFs, so we're going to do a little review. We'll go ahead and title your paper. Factoring the GCF. And let's remember what a GCF is. It's the greatest common factor. Okay, and remember that a factor is the number that multiplies to make our number. Okay. Now there are many different ways that you can determine your GCF. You can go through and list all of your factors. The most efficient way is to find the prime factors of each of our numbers. So let's just jump into an example. What is the GCF of 18 and 30? Okay, so again, you can go through and you can list the factors. Okay, so 1, 18, 2 and 9, 3 and 6. And you could do that for each number, and you could find, the largest number that they both have in common. The other option would be to write a multiplication expression that equals 18, but we've got prime numbers, kind of like if you were to create a factor tree. And what you get for 18 is 2 times 3 times 3. So where I got that is if you were to create a factor tree, you would end up with basically the prime factorization of 18 would be 3 times 3 times 2. That's all we did here. So we just found the prime factorization of our number, and we'll do the same thing with 30. If we did the prime factorization of 30, we would get 2 times 3 times 5. And then all we have to do is we look and say, okay, well, I have a 2 in common, and I have a 3 in common. 2 times 3 equals 6, so my GCF would be 6. Okay. Now, if you had made a list of all of the factors, so if you had done this, and you don't have to write this part down, but if you had said, 1 and 18, 2 and 9, 3 and 6, and then for 30, 1 and 30, 2 and 15, 3 and 10, 5 and 6, then you would go through and you would try to find, we have common, 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 and then the common factors end. This 6 is the greatest, so it would be the GCF. Okay, just depends on which process you're more comfortable with. However, having said all that, this is just review of what the GCF is, right? It's a factor that the two numbers have in common. Okay, now that's not really what we're not working on that simple of a process. We're actually applying this to polynomials. So I want you to copy down the definition of the GCF of a polynomial. Okay. And it is the largest integer and highest degree of each variable that will divide into each term. Okay, so the largest integer is what we just did in this last example. So the part where it says like the largest integer, within our polynomial, you would look at your coefficients or constants, and you would look for that GCF, okay, largest integer, 6. The next part talks about the variables within the polynomial. And we'll see this in some examples, but the part where it says the highest degree of each variable that will divide into each term, basically what's going to happen that you'll see as we kind of go along, but it really ends up being the lowest degree variable, which seems strange because this says highest degree, but we're going to come back to that. But it does end up being the lowest degree variable. And like I said, it does sound like that's the exact opposite of what's written here. The difference is the highest degree of the variable that divides into the term is more of the process to find the GCF of the variables, and it ends up actually being the lowest term. You'll see. So just kind of hang with me. I know that's a little strange, but just kind of hang with us. You'll see as we go through our examples. Okay, so a couple little notes. Okay, so think of factoring as the reverse of the distributive property. And this is something that you would have done in a previous grade where you undo the distributive property. It would have, I believe it's a 7th grade standard. And you don't need to write this down, but for example, if you would have been given something like, I don't know, 2x, or actually, 2 plus 4. And you would have rewritten it as 2 times 1 plus 2. You would have found a common factor and divided it out. This would have been something in probably 7th grade where you were learning about the distributive property the first time, and you saw this expression, and you would practice the distributive property, and then there was probably a point where your teacher had you do the opposite and factor out the number that would be outside of the distributive property expression. Depending on your teacher and what you are working on, this may not look familiar, and that's okay. But just so you can kind of have a reference point in case you've seen it before. Okay? So it's like the reverse of the distributive property is basically what we're doing here. Another piece of information, there's something called a prime polynomial. And it is a polynomial whose GCF is 1. All right, so definitely make sure you get these 2 pieces of vocabulary down. Going to be important as we work to be able to hear or understand what words we're using as we use them. All right, so let's take a look at our first example. And we're going to factor out the GCF of this expression. So our expression is 18x squared minus 50y squared. So the first thing we're going to do is we need to find the factors of each of these terms. Okay, so the first thing we're going to do is find the factors of each term. Okay, so let's find the factors of 18x squared. So remember, we're just getting, we don't want to write a list. And I know at that first example, I showed you the two ways that you could have approached the GCF of 18 and 30. But now that we're looking at expressions with variables, possibly constants, possibly, with coefficients, we want to come up with prime factorization. Okay, so we want to write the prime factorization. Again, that's the multiplication problem that has all prime numbers. Okay, so what prime numbers multiply to make 18x squared? All right, so the prime factorization of 18, which we actually have from above, is 2 times 3 times 3. Then I'm going to take the x squared and I'm going to break it down into x times x. Okay, so I just got the prime factorization of 18x squared. And remember, prime factorization means each of these factors here is a prime number. Or, in other words, the only thing that multiplies to make that number is 1 and itself, which is why we broke down the x's. Okay, and then let's do 50y squared. 50 is going to break down to 2 times 5 times 5. And the y squared is going to become y times y. And remember, if you're struggling to get the prime factorization, you can always go off to the side and do a factor tree, right? If you don't remember how to do a factor tree, go to YouTube and find some assistance. So now we're going to go through and we're going to find the greatest common factors. So which factors do these two terms have in common? Well, they've got a 2 in common and nothing else. So nothing else is in common. So what's going to happen is we're going to divide a 2 out of this expression. Okay, so this was step 1. Step 2 is we're going to divide the common factor out of the polynomial. Okay, so what's going to happen is I'm going to take that 2 and it's going to be divided out. So it's going to come outside. And then if I take a look at what's left, I'm going to rewrite what's left as my expression. So 3 times 3 is 9. Times x is 9x squared minus 5 times 5 is 25 times y, 25y squared. And if you look, two divided by 18x is 9x squared. 2, when I divide out my 50y squared divided by 2, I get negative 25y squared. Okay, so off to the side, what we're going to do, just so that you have notes, and I said it wrong a second ago, we were looking at 18x squared divided by 2, not 2 divided by. So all we did was we said 18x squared divided by 2, and we got 9x squared. Then we said 25y squared divided by 2, 50y squared divided by 2 is 25y. And that's where we got these two terms. It's going to stay subtraction because my original expression was subtraction, and I divided out a 2. And that's our final answer. So step 3 would be write the factored polynomial. Okay, let's look at another example. Factor the GCF. Okay, and our problem is 3g to the 8th plus 3g to the 5th. Okay, so refer to the steps we just wrote. Step 1 was to list our factors, right? So our factors of 3g8 would be 3 times g, and we're going to repeat the g 8 times. Let me double check I have 8, and I do. And then 3g to the 5th is going to be 3 times, and then g times itself 5 times. And then we're going to go through and select our common factors. So I have a 3 in common, and then I'm going to have 5g's in common. So in this case, my GCF is 3g to the 5th. That is what gets divided out of my expression. So we're going to divide 3g to the 5th out of each term. Okay, so on the outside here, I'm going to have 3g to the 5th, and then I'm going to write what's left from each term of my expression. So if I look at my 3g to the 8th, these 3g's are all that's left. G times g times g. So I have g to the 3rd left. Plus, now if I look at my last expression, I have nothing left, right? All of my terms, or excuse me, all of my factors were used. So I would just write a 1. Now you can always double check your work by applying the distributive property. Okay, so if I distributed, I would see that I would end up with my original expression. So that's a way to check yourself. So if you're ever unsure if you did anything, if you made a mistake, you can distribute to check. Okay, so there's absolutely a way that you can make sure you have the answer right before you even move on. Now, I want to go back for a second to one of your definitions that we talked about at the very beginning. Okay, I want you to look at this section here. Highest degree of each variable that will divide into each term. So that is saying we're looking for the GCF with our variables. Okay, so highest degree of each variable that will divide into each term. That's saying we need the GCF of the variables, which in the last example we did when we wrote all the g's out and we grouped to see, okay, well, each term has 5 g's in it, or 5 g's multiplied. Now this part down here where it says ends up being the lowest degree variable, let's look at that for a second. If you look at our expression here, g to the 5th is our lowest degree variable. And if you look, g to the 5th is what was divided out. So that's what it means when I said in the notes, the lowest degree variable. That ends up being what gets divided out. Okay? Just wanted to make sense of that definition before we moved on. All right, we'll go a little bit faster here. Example 3. $13 a squared c plus 20b. So we'll go through and we'll get our GCF of each. Let's get the GCF of 13a squared c. Well, 13 is prime, so I'm just going to have 13 times a times c, and 20b. Well, 20 is 4 times 5. 4 is not prime, so I can say 2 times 2 times 5 times b. Now, if you look, do we have any common factors? No. No common factors. So what that means is that this is a prime polynomial. So in this case, your answer is the original expression. There are no common factors besides 1. This is a prime polynomial. So if that's the case, this expression is your answer. Okay, let's look at another example. Okay, we're going to factor GCF, negative 100z to the 9th minus 50z to the 6th plus 75z to the 3rd. Okay, now our factor list is going to be pretty long, so instead of writing to the side, I'm going to write underneath. All right, so negative 100z to the 9th is going to be negative 1 times 2 times 2 times 5 times 5 times z, and we're going to be multiplying 9 times. Let me double check my count. Okay, perfect. Now you'll notice I put a negative 1 up front. You're going to see why that's important kind of as we work through some examples and during this example. If there is a negative 1 to factor out, we want to do that. Okay, so the next part, and this is something we didn't do in one of the previous examples, but we're going to do it now and you'll see why in a minute. But this minus 50 z to the 6th, when we do our GCF, we're going to count that as negative 50 z to the 6th. Okay, so negative 1 times 2 times 5 times 5 times z 6 times. Now, I already had these numbers factored. Again, you're going to want to make sure you go through and factor the way that makes most sense to you. Okay, and our final one is 75 z to the 3rd. So there is no negative I need to worry about here. So we just have 3 times 5 times 5 times z times z times z. Now, there are some 2's involved here, so please make sure that when you're working through these, you either add this little mark to your z's so that you know those are z's, or make sure you're drawing them nice and sharp, or maybe like I'll go back through and rewrite my 2's and make them more loopy. But please make sure you find a way to decipher between the z's and the 2's. You're going to get yourself into some trouble if you don't. Okay, so now if we go back through, we're going to find common factors between all 3. We're not looking at just 2 anymore. So I've got a 5 in each, I've got another 5 in each, and I'm going to go down to my lowest degree. It's 3 z's, right? Z to the third is my lowest degree, and that's going to end up being the factor of Z that I divide out. Because if I have Z to the third is my lowest degree, I know that all of my other terms, the Z's at least, okay, so all the other terms that have Z's will have Z to the third within the power. Okay, so my GCF is going to be 25Z to the third. So we're going to take the GCF, and that's what we're going to write first, 25Z to the third. Okay. And then we're going to go through each term and write what we have left. Okay, so you can go up here and, try to divide the 25Z to the third out and see what you have left. But we do have our factors that are left over, and we're going to use those leftover factors to determine what's inside of our parentheses. -1 times 2 times 2 is -4. And we've got Z to the sixth. And if we look at our next term, -1 times 2 is -2. Z to the third. Oops. And finally, our last term is just a 3. Now remember to check yourself. If you look at this and you're like, okay, I don't know for sure if I'm right. Did I do everything how I was supposed to? You can always check yourself by distributing. Okay, so you can always distribute to check. Okay, that's always an option. Now, there is one other way we're going to look at this for a second. You can factor out a -1. Okay. There are times strategically where this will be what you want to do. Sometimes it's believed that if your leading coefficient, if you remember, this is our leading coefficient. If your leading coefficient is negative, you do want to divide out or factor out a -1. Okay. Not always, like I said, strategically, sometimes it's better. Other times, like mathematics etiquette, you divide out the -1 if it's a leading coefficient that's negative. But I want to show you what you would do. So if this is the case, if you look at this and say, okay, my leading coefficient is negative, so I need to divide out the -1 as well. You continue to work the way we did. All that's going to happen is I'm going to divide a -1 out. So everything is going to become the opposite. So if I divide a -1 from each of my terms inside, what's going to happen is my 25Z becomes -25Z to the third. -4Z to the sixth here becomes +4Z to the sixth. -2Z to the third becomes +2Z to the third. And +3 becomes -3. Okay, that will come in handy from time to time strategic wise, just so you know. The other thing to remember is that note that I made up at the very beginning about when you're factoring out, it will end up being the lowest degree variable is what gets factored out. And if we look, Z to the third is my lowest degree variable. Well, my lowest degree Z, and Z to the third is what was divided out. Okay, so keep that in mind as you work as well. Okay, so our final answer could be either of these. Right, and our last example, oops. I want you to try on your own. We'll see it's how you do on this one. So 18 x to the fifth minus 24 x to the fourth plus 10x to the third minus 6x. So pause your video, and I want you to try this on your own. I'm going to work through it, but I'm going to work through quietly, so you can just let the video play as you work as well. Okay, so hopefully you got the same thing I did. Couple things. The x that was divided out is actually our lowest degree, right? X to the first power, x to the first power. Don't forget the negative ones for the negative 24x squared, or to the fourth, and the negative 6x. Don't forget to, remember that when you go back through and get your expression that was inside here as well. So that's it. That was a long one. Thanks for hanging with me, and that's it.